Hello, everybody. I'm Andreea Deac, PhD student at Mila University of Montreal. And today I'm happy to present a talk that I think will be interesting to all problem solvers among us. This is called Neural Algorithmic Reasoning, and we'll talk about how to combine classical algorithms and neural networks. This is, as you might think already, there are two well-known approaches to problem solving, each with their own benefits and drawbacks. So algorithms are trivially strongly generalizable. You can apply them to different sized inputs, and they will still work. You can compose them if you have different functions, subroutines. You can use them together, chain them. They have guaranteed correctness, and they are interpretable. They have interpretable operations. We always know what they're doing. However, their inputs must always match a specific format, and they're not robust to task variations. On the other hand, the more recent go-to, the neural networks, they can operate on raw inputs. They can generalize on noisy conditions. So even if our inputs are not precise, they will still work. They can be reused across tasks. But a downside is that before getting a neural network to perform well, we usually require a lot of data to train them, to get them to a good performance. They are also unreliable when extrapolating, and they lack interpretability, although that's actively being worked on. You might notice that these two approaches have attributes that are complementary, and what we might want is to get the best of both worlds. So this is what today's talk is going to be about. And I'll start by talking about a problem that is quite simple. Most computer science students meet it at some point or another. So if we have a weighted graph with a specific source node of interest, and we want to compute all shortest paths from this node to the other nodes in the graph, we can do this by using some dynamic programming algorithm, for example, Bell-Manford being one of them. And recently, there was the paper called Neural Execution of Graph Algorithms, where a team of researchers tried to propose a neural network that can achieve the same goal. So this was a graph neural network in particular that was supervised on intermediate outputs of the Bell-Manford algorithm. So this is also known as strong supervision at every step of the iteration. And you can see that the operation in the dynamic programming algorithm aligns quite well with the message passing update rule in a way. So this observation was something that was explored more in a concurrent work, where they discovered that graph neural networks align well in general with dynamic programming algorithms, not just Bell-Manford. And some other findings were pointed out. So, for example, this strong supervision I was talking about is actually quite important to a good performance of the graph neural network in imitating the algorithm. It requires things like a different aggregation, the max aggregation, to perform well, which aligns again with what we know the dynamic programming algorithm does. More recently, there's also been a lot of work on proposing better architectures, for example, for achieving some classic computational goals, and some even more recent insights. For example, linear algorithmic alignment is highly beneficial, and if we learn multiple algorithms in a multitasking way, this can also improve performance. So this is also very useful, especially if we want a component that learns multiple algorithms, not just one. So this led to a blueprint being proposed by Veličković and Blundell in patterns. So under the name of neural algorithmic reasoning, we have this blueprint, which starts from the assumption that if we have a task where we know an algorithm could be useful to solve this task, then we can pre-train the processor on some abstract inputs to learn this, how to execute this, how to simulate this algorithm. And then we can take this processor and plug it into our natural pipeline. So in the case of navigation, where we're interested from getting from point A to B, C, or D, we might want to use something like Bellmer-Ford, which computes shortest path to see what is the best way to get somewhere, to navigate. So keeping this blueprint in mind, you might be wondering, does this work in practice? Has this been used in some tasks already? So in this talk, I'll talk about how this was used in reinforcement learning. Our proposed agent, Excelvin, was done in collaboration with Petar Velichkovic, Ognjen Milinkovic, Pierre Bacon, Jian Tang, and Mladen Nikolic. And even more recently, this was also explored, this blueprint was also explored in a self-supervised learning setup in the paper named Reasoning Modulated Representations, about which I won't have time to talk, but I recommend you go check it out. So to jump straight into it, in a reinforcement learning setup, we have an agent that acts upon a word and receives observations back from this word. This agent can decide to build a plan and update this plan based on the observations, a plan that can then be used on deciding which actions to take. So formalizing this a bit, this is usually found under the Markov decision process framework, where we have a state space, an action space. We have the transition matrix. So what's the probability of getting to a state S prime, given that we're in a current state S and we take a specific action A. Also reward. So what's the reward that the agent will receive by doing action A in state S? And the goal is to find a policy pi that tells me what is the sequence of actions I need to take in order to optimize the discounted cumulative reward. So get as much reward over a longer time horizon as possible. So policies that act purely through adapting to rewards are called reactive. And in many cases, to get them to work well, they require a lot of data and are quite slow to adapt. And planning is something that was proposed to ameliorate these issues by maintaining an explicit model of the word. So what this means is that we would have a state transition model and a reward model, which would usually train from some observed trajectory. So having the agent act into the world and gather some data. And using these models, a planner can simulate the effects of actions before taking them, which is very important and comes with some important benefits, as we're going to see now. So some of these benefits, well, the first one is data efficiency. And this is very important if we're planning to use our agents in real world, where we don't have access to millions of frames as we do in the case of games. So if we have the good model, that would mean that we'd have to interact less with the environment in order to get a good policy. Then strong models will also allow us to adapt to unseen situations. So that is very important if anything is changing in the environment, for example, and also very important for safety reasons, because if we have a strong model predicting if some action would lead to an unsafe outcome, that means that we can avoid taking that action to learn that would happen. So this is quite important from a safety considerant. It will also allow us to account for external factors such as human interactions. And in fact, this was already used in game playing, AlphaGo, which you've probably heard about, and across the sciences, for example, for chemical synthesis. Planning has some theoretical results that are very encouraging. So if we had a perfect model, this would allow us to plan for perfect policies. And this is quite important. One algorithm that is very useful for planning is value iteration. This is a dynamic programming algorithm, which is, we'll see why it's important in a bit, that can allow us to perfectly solve a reinforcement learning environment. So what this does is it computes values of states based on the values of neighboring states. And it starts with, for example, a random estimate and gradually improves these estimates until it reaches an optimal solution. So this is guaranteed to happen, which is very convenient. And if once we compute this optimal solution, then the optimal policy can be found just by taking the actions that maximize these values. So once now that we know about this very useful algorithm, well, we could think, what can we do with it? So could we actually use it in a reinforcement learning environment? That would be a great thing. Assuming, for now, we'll assume that we have the reward function and the transition matrix. And in a bit, we'll talk about what to do when we don't have these two things. So we assume the transition matrix is fixed and known. By known, for example, each state has known neighbors, up, down, left, right. The actions are deterministic. And computing value, doing value iteration would amount to computing sums of neighboring values. And this might already remind you of something that's familiar. So convolutional neural networks are quite well suited to computing this convolution-like computation. And this idea was leveraged in value iteration networks, which got a Best Paper award with NeurIPS in 2016. So to summarize, assuming the MDP is discrete, fixed, and known, they perform value iteration computation by stacking shared convolutional layers. And while this is great, it has the downside that this is quite restricted in the sense the MDP needs to be discrete, fixed, and known. And GVINs already take a step towards more general cases, extending to the case where the MDP doesn't have to be agreed for it. But it is still fixed and known. So in that case, like so far, we didn't need to estimate the transition model. We didn't need to find what the P would be. And we didn't have to deal with continuous state spaces either. But what would happen if we didn't know the MDP? Well, we can think a bit. What would a human feature engineer do to use value iteration, which we've seen is a very useful algorithm? So the human feature engineer would take the gain frame, which we call the natural input, and compute some abstract input from it. On each, they would be able to run the value iteration algorithm to get abstract outputs. However, we've seen that deep learning does a very good job when we don't have to manually compute features. So we'll use some of this insight and have an encoder that bypasses this part of human engineering. So this would take our natural input to an embedding, and that is great, but that would still not be everything we need to run value iteration if we didn't have the transition matrix. For that, we can use a transition model to build this local MDP that we need in order to run value iteration. And this was already studied quite a bit, and there exist many popular methods for training this transition model. I'll just name one of them, which is what we used in our proposed agent. So contrastive learning is one way of training T, and this would mean training T to discriminate between true next states and some fake next states, some randomly sampled S tilde. So if we have a transition model that learned how the next states S primes will look like, this transition model can be used in a generative manner, in a way, to build the tree over which we run value iteration. So if we have this tree, we have the P, but we still don't have the reward model. So for now, we'll assume that this is given. We'll assume that the nodes in the tree I've previously shown are known, and that would be everything we need to run value iteration directly over this tree. And this is exactly what was done in TreeQN and value prediction networks. And to summarize their architecture, we have the state and the encoder, which is then used repeatedly to build a tree. And in this tree, the values are estimated in each of the nodes. And then this can be used for value iteration to do the backup and use this. So to summarize a bit what I've talked about so far, we mapped our natural inputs to the space of abstract inputs using an encoder. Using a transition model, we built a local MDP, and we estimated the rewards in each of the nodes in the case of TreeQN. And this allowed us to run value iteration directly on this tree. And this is quite convenient because it aligns in the direction of implicit planners. That is a very neat direction. I recommend you read more about if this sounds like something that would be up your alley. However, doing this running value iteration directly on this tree presents us with the algorithmic bottleneck. So real world data is often incredibly rich, and we still have to, in the previous case, we still had to compress it to scalar values. So the value iteration solver committed to using the scalar the model predicted and assumed it was perfect. And if there is insufficient data to estimate the scalars, then the algorithm is running on incorrect inputs. So incorrect outputs will very likely go out. So this means that we need to have correct inputs for the value iteration to do what we want. And we hit data efficiency problems again, which is precisely what planning was supposed to solve. So trying to avoid this bottleneck of the algorithm gives a perfect solution, but in a suboptimal environment, we propose our agent Excelvin, which is aimed at breaking the bottleneck. And the main idea behind it is that neural networks derive great flexibility from their latent representations. They are inherently high dimensional, which means that if any part of that high dimensional vector is predicted poorly, then the rest of the vector can be used to compensate and still lead us to a correct answer. So to break the bottleneck, we replace the value iteration solver, like we train the value iteration directly on the scalars with a neural network. So that combination I was mentioning earlier on. So what we'll do is we'll have a neural network between natural inputs and abstract inputs, that encoder, and we'll also have a neural network between our abstract inputs and abstract outputs instead of having the value iteration algorithm. So how do we do that? We do it by pre-training a graph neural network to perform value iteration style computations on synthetic graphs, so something we can easily generate. And then we freeze this, we keep this as a trained reasoning component and deploy it within our planner. And you might remember, as value iteration is a dynamic programming algorithm, this is quite easy to do, thanks to this algorithmic alignment that was pointed in the iClear20 paper. So putting all together, our Excelvin agent looks up like this. We have the state, our neural network, encoder taking to a latent representation, our transition model that is used to build that local MDP that in the case of value iteration networks was assumed known, but now we don't have. As we won't have in most of the reinforcement learning environments we're looking at. Then after we build this tree, we use our pre-trained executor that we pre-trained on synthetic graphs. And we use this to predict values and actions and plug this into your reinforcement learning algorithm of choice, in our case, PPO. So to look a bit on the empirical side, our agent is in green. We compare it with A3C, which is the model I talked about earlier, which actually runs value iteration in scalar space rather than in latent space, as XLVin does with our pre-trained executor. And we also compare with a component that is just model-free, doesn't have any planning component. So we see that usually in a lot of the cases, the XLVin and the A3C do better than the PPO baseline. And something else that is very interesting to notice is the XLVin does better than A3C, particularly in the first half of the training. So it does well in low data cases, which is one of the main things why we're looking at planning in the first place. So this is quite an encouraging result. To draw some conclusions, we presented this blueprint that is applicable if we know a specific algorithm will be of interest for solving a real world task. So we say that real world solutions can benefit from combining classical algorithms with neural networks, and this is one way of going about it. Then we build on the findings that graph neural networks are particularly well suited to imitate some algorithms, in particular dynamic programming algorithms. And one example is Bellman forward, and other is value iteration. Value iteration, which is a very useful algorithm in reinforcement learning, as it allows us to plan, and it can lead to perfect plans. And using this component that learns to imitate value iteration in a reinforcement learning agent led us to find that it can have great benefits, for example, having good performance in low data cases. Thank you for listening. Some of this work was already presented in some nice articles, so do check them out if you would like to see more about this. And of course, these were presented in research papers. Neural Algorithmic Reasoning and Neural Algorithmic Reasoners are implicit planners. I'll also link them here if you'd like to read more about them. Lastly but not least, I'm happy to take questions. And in general, if you have thoughts, feel free to send me an email. Thank you.